This is our first video on circular motion. In uniform circular motion, which I'm going to abbreviate from now on as UCM because it's quicker, an object is traveling in a circle at a constant speed. In uniform circular motion, the magnitude of the object's acceleration is equal to the mathematical expression A is equal to V squared over R. This is a very important equation right there. V squared over R is the acceleration of the object. This acceleration is termed centripetal acceleration and is always directed or pointed toward the center of the circular path. So a centripetal acceleration, the equation for a centripetal acceleration, you see the equation. Perhaps I should put a little subscript C there if I want. I can do that. Centripetal acceleration is equal to the speed of the object at that moment squared divided by the radius of the motion. In terms of a quick picture, if an object is traveling in a curved path like that, when the object is right there, when it's 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 there, the acceleration vector points towards the center, and it is always at right angles to the velocity. There are your acceleration vectors, centripetal acceleration, always towards the center and being perpendicular to the velocity. So let's try a problem here. We have a person who's on a roller coaster, and it's going over a high point on the ride, and this portion of the ride has a radius of r. We're traveling this fast, and there's the person having a mass of m, and we want to derive an expression for the force that the seat exerts on the person. In which direction is the seat exerting a force on the person? Upward. We need to find the normal force. We always start with a free body diagram. So there's the mass right there. We've got mg acting downward, and we have the normal force acting upward. Now, check it out. In this case, the normal force is going to be less than mg. And here's why we know that. Look at the picture in the upper right. Look at the curve. This person has to be accelerating that way. Because of the curvature of this thing, the acceleration has to be in that direction. It can't be up. It's got to be towards the center of the circle. Therefore, if you look at my free body diagram on the left, mg necessarily has to be bigger than Fn. Let's now use Newton's second law. The net force is equal to the mass times the acceleration. The net force, mg is bigger, so I'm going to go mg minus Fn is equal to the mass of the object times its acceleration. Okay, we are traveling in a curved path. We just said on the previous paper that a centripetal acceleration is numerically equal to the speed that the object is traveling squared divided by the radius of curvature. Therefore, the normal force, can we do this? I put that over there and put that over there. I think it's going to be mg minus mv squared over r. Should we make that a little bit prettier, we can factor out an m times g minus v squared over r. How about number 2? Derive an expression for the lowest speed the car could have that would launch the person off the seat. All right, launch the person off the seat. What does that mean? If the person is launched off the seat, what's the normal force? There is no normal force. The seat isn't touching the person anymore. The normal force would be 0. So to solve this second part, we're going to set the normal force equal to 0 and solve for v. V equals what? For Fn equals 0. All right, can we do that? I put a 0 there, divide both sides by m, and that gives me nothing. So I end up with basically G is equal to V squared over R. So I think the minimum V is going to be G times R square rooted. If it's going that fast, this person is going to start to rise off the seat. We don't want to go faster than that. Does the person's mass affect this minimum speed? Well, look at the equation. There's no mass in there. No. Massive person, not very massive person, makes no difference. That speed would be the same for that person to start being raised off the seat of that roller coaster car. I hope they're buckled in.